Hello everyone. So today we will talk about Mohr's circle. I believe everyone has seen a lot of different circles. All circles look the same, but they may have different functions. So today we selected the one. We picked the one which we can call it a Mohr's circle. And we will see how can we use a circle to represent all possible stress status at a point. So here are the objectives today. We will draw more circles to find the principal stresses and the maximum stresses at a point. Okay, then we will start to talk about transformation of strain. So in the last lecture, we have shown several equations that we can use for stress transformation. Let's see, we start from a random stress status, which includes several components. That is sigma x, sigma y, the two normal stresses, and tau xy, tau yx. Those stresses, those shear stresses, will have the same magnitude, right? So this the stress status can be denoted by sigma x, sigma y, and tau xy. Okay, you just have these three components at a random point. Then if you rotate it by angle theta, right, then from this initial stress status, you can get another one, which is denoted by sigma n, sigma t, the two normal stresses, and a tau nt. Right. So here, just after transformation, you get sigma n, sigma t, tau nt. Right. So you can use these three equations. These three equations we learned last time to achieve this stress transformation. Right. We also introduced a concept called principal stresses. Right. Principal stresses are the maximum and minimum possible normal stresses at a point that you can derive it, calculate it from the initial random stress status. Then you will get the principal stresses. At this status, you will have principal stress P1, sigma P1, sigma P2. These are the maximum and minimum possible normal stresses, and tau equals 0. Okay, these are the characteristic at the status of principal stress. Okay, you do not have any shear stress at the principal stress plane. Then you can also find you can achieve this principal stress status from the original state by a rotation of theta p. Right, here is the theta p. By rotation of theta p, you will get the status of principal stresses. Then how about the maximum shear stress? You just rotate it to the other direction, to the opposite direction, by angle equals theta p minus 45 degree. Okay, this is from here to here, or from the original status to the opposite direction by theta s equals theta p minus 45 degrees Celsius, or theta p plus 45 degree to that direction. Okay. So here, at the status of maximum shear stress, you will have the same the same normal stress components on the two directions. Right. So you have sigma average, tau max. Okay, so here the tau max equals the difference between two principal stresses over 2. Right, so the sigma average equals the average value of the sigma x and sigma y. in the initial states. Right? Those are what we derived last time. And you can see the characteristics here in these equations, and these two constants. Okay, those are all important features that you can use to simplify your calculations. So today we will show the Mohr circle. So you will see that all of these equations, when you put all of these equations together, you get a circle. Okay, meaning that we can use a circle called Mohr circle to represent all possible stress status at a point. So first of all, let's see how can we do this. How can we represent all status and find the principal stresses at a point using a Mohr circle? Okay, let's start from a random stress element. Here is a random two-dimensional stress element. You have a tau xy. You have sigma x, sigma y. Right? So here is a random stress element where you have these three components: sigma x, sigma y, and tau xy. Then we can draw these points in a coordinate system. Okay, let's draw a coordinate system here. This is a coordinate system sigma tau. Okay. So the x-axis represents the normal stress, and the y-axis represents the shear stress. Okay, then in the first step, we can find these two normal stresses. First of all, on this sigma axis. Okay, this is our first step. We will find the two normal stresses on the sigma axis. Okay, what are the two normal stresses? Is sigma x and sigma y. Okay, let's assume that here is the sigma x, and here is your sigma y. Okay. Then the second step, we will find these 2 points. Find these 2 points, sigma x, tau xy, and sigma y, negative tau xy, and connect them. Okay, so here let's find the sigma x, tau xy first. You just start from the sigma x, tau xy. Okay, here is the point sigma x, tau xy. And then Here is your point sigma y negative tau xy. Then we can connect these 2 points. We connect these 2 points, you get a line, right? So then we will just use this line as diameter. Use the line as diameter to draw a circle. Okay, so this is not an easy part. Let's connect these two points and use this line as a diameter to draw a circle. Okay, so get a pretty good circle. So let's analyze this circle. In the next step, step 4, here is a question: where is the center? Where is the center of this circle? Where is the center of the circle? I mean, can you find the coordinates of the circle? Coordinate of the center of the circle? It's right here, right? Let's call it C, right? This is the center. What is the coordinates of this circle? The x coordinate must be the average of sigma x and sigma y, right? So that is sigma x plus sigma y over 2, 0. Right? So this is the coordinates of the center. That is sigma x plus sigma y over 2, 0. This is the coordinates of this center point of the circle. Then how about the radius? Okay. What's the radius? R equals what? Okay, here is the radius. Right, let's denote it using a R. You can see that actually you can determine the magnitude of R from this triangle. Okay, from this triangle. And we can draw this triangle here. The triangle here, the dimension of this side is what? It's just tau xy, right? It's a tau xy. How about here? Here is actually sigma x minus the coordinates of the center, sigma x plus sigma y over 2. Right? And that equals sigma x minus sigma y over 2. Then just from this triangle, that you can get that the R equals sigma x minus sigma y over 2 square plus tau xy square root. Right? So this is the radius of this circle. Then in the next step, we can try to find the principal stresses. Okay. Let's try to find principal stresses, sigma p1 and sigma p2. What are the definitions? Okay, how did we define principal stresses? These are the maximum and minimum, okay, normal stresses at this point. Just look at the axis of normal stress, the sigma axis. What are the maximum value that is possible? And what is the minimum value that is possible on the circle? Okay, obviously here is your maximum value. Okay, this is the sigma p1, and this is your smallest value, that is sigma p2. So just using the center coordinates and the r, how can you determine sigma p1? What is sigma p1? That is actually the coordinates, x coordinates of point C plus radius of the circle, right? So that is sigma x plus sigma y over 2 plus square root sigma x minus sigma y over 2 square plus tau xy square. Right? Then how about sigma p2? Sigma p2, the minimum possible normal stress at this point. That is from the center minus r. Right? So here you will get sigma x plus sigma y over 2 minus square root sigma x sigma x minus sigma y over 2 square plus tau xy square. Right? Then you can go back and compare these two equations that we just derived, to compare them with the equations in our summary slides. Okay, go back to compare them. You will see that you get the same equation. Okay, meaning that you can easily derive these equations to calculate, to determine the principal stresses based on the Mohr circle. Then the next question. What is the maximum shear stress? Tau max. Okay. Just look at the circle. Just on this circle, where is the maximum possible tau value? Okay, here is your tau axis. Right. So what is the maximum tau value? Obviously it's here. Right? Here is the maximum tau value. So what is the magnitude of this tau max? Okay, this is tau max. So it's easy to determine it. Actually, the tau max here just equals R, right? And this is just a radius, okay? It equals R. Therefore, it equals sigma x minus sigma y over 2 square plus tau xy square. Or it equals sigma p1 minus sigma p2 over 2, right? Since this sigma p1 minus sigma p2 is just a diameter, right? Half of it is the radius. Okay, then how can you get sigma p1? How can you get the maximum stress from the original random stress status? From the original stress status. Okay, we know that as defined last time, we know that to achieve this, to achieve the principal shear stress from an original random shear stress status, you need to move it or turn it, rotate it by theta p, right? So this is the answer. Actually, you need to move or rotate by theta p. Right? From this circle, from the Mohr circle, obviously this can be achieved by rotation it. Here is your original status, right? Original status here, and this is your original status, right? To achieve the principal stress status, you just need to turn it clockwise from here to here, right? Here you will get it. This movement meaning that you rotated it by theta p, but the value of this angle here is actually 2 times theta p. Okay, on the circle, on the real element, you're rotating it by theta p, but on the Mohr circle, you rotated it by 2 times theta p. Now let's look at how can we determine the 2 theta p. Okay, since it's in the same triangle as shown here, right? So we can use this triangle to calculate the values of the theta p. Right. So tangent to theta p equals, okay, in this triangle equals tau xy over here, okay, over sigma x minus sigma y over 2. Okay, so this is the equation. Okay, you can see this equation in this summary slides. Actually, we proved it again. It's easy in the Mohr circle to derive any equation, to derive any key equations you will use for the determinations of the principal stresses, maximum shear stresses, and principal stresses, etc. Okay, you can just derive all of these equations from the Mohr circle. Okay, the last step. how can you get tau max from the original status? So from last lecture, we know that you should just move or rotate by pi over 4 or 45 degree minus theta p, right, to the opposite direction. So that means from the original status, you need to move it to the other direction. Right. So this angle on this Mohr circle will be two times of this value. So this value will be 2 times of it will be pi over 2 minus 2 theta p on a Mohr circle. Okay, so this angle here is actually pi over 2 minus 2 times theta p, right? Then at this point, the sigma equals sigma average, or the average value of the two normal stresses at the original states. Okay. That are how did we derive the Mohr circle. Okay, so you can review the whole process to try to understand the whole process, and then you can find that it's actually easy to derive all of these equations, all of the features from this Mohr circle.